first presentation this morning is let's introduce Chris Dyck, who's a senior bridge engineer at COWI North America. He's going to be talking about fatigue retrofits for 2 suspension bridges in the Patagonia region of Chile. So let's welcome Chris.
Good morning. Great to be here in Phoenix. It's quite a departure from the weather we left up in Halifax there with snow. My name is Chris Dyck, as Matt said. I'm a senior bridge engineer at COWI North America Limited. Today I'll be sharing with you a project we recently completed in the southern Patagonia region of Chile. So this background photo that you see here was captured by my colleague when he went down for inspection in September of 2021, showing the beautiful location in the mountains where the project took place. So just a little bit about COWI. We got a long history working on all types of infrastructure. Been in business for 90 years, about 7,500 individuals around the world. We've got offices throughout North America as well. I work out of COWI Halifax in Nova Scotia, Canada on the East Coast. But obviously with remote work tools, we can cover the world now. So this project is evidence of that. Analysis and design took place in Halifax for a project in Patagonia, southern Chile. Specialized in bridge infrastructure at all scales, from small rehabs up to the longest suspension bridges in the world, tunneling and offshore. So at the right of the slide here that I'm showing you, many of you are probably familiar with this. This is the nearly completed 1950 Çanakkale suspension bridge in Turkey. Designed by COWI, currently the longest suspension bridge in the world with main span of 1.26 miles and overall suspended bridge length of 2.21 miles. Back to the talk. I'll be introducing our client for this project, giving a description of the bridges and the fatigue fracture event that occurred. It's pretty interesting. I'll be touching on our inspection approach, load testing we did, the finite element model developed, and its theoretical behavior versus the field result. We grounded the model. We'll talk about the impact of the bridge joints on the fatigue behavior, and then I'll conclude by discussing what we're doing about it. COWI was hired by our partner on this project, RNZ Engineering, out of Santiago, Chile, as a structural consultant. RNZ is an engineering consulting company. They operate in 5 Latin American countries, including Chile, Colombia, Peru, Mexico, and Paraguay, with about 2,000 staff. So they were in turn contracted by the Chilean Ministry of Public Works, who initiated this project following the fatigue fracture event. So the entire project, from reporting to inspection and drawing notes, etc., is conducted in Spanish, which has been an interesting element on this project. Bridges are in a beautiful area of southern Chile. They're located along Route 7, which connects areas to the north with Patagonia to the south, and are on the only route through this area. So they're therefore considered critical infrastructure. You can see on the right a dark gray line. This is the border between Chile and neighboring Argentina. Unless drivers and truckers want to cross an international border and travel through a neighboring country, with all the hassles that can go with that, they must travel Route 7 and cross these 2 suspension bridges. The first bridge is simply supported truss span on hangers with a main span of 427 feet, 53-foot tall towers. Single lane with 2-way alternating traffic. Main cables are wire ropes with steel core. Second bridge is also simply supported truss span on hangers, 66-foot approach span. Main span is a bit longer, close to 500 feet, and the towers are correspondingly also taller at about 60 feet. Single lane, 2-way alternating traffic. These 2 bridges are very similar in their construction and detailing, which is one of the reasons they were lumped together. So in September of 2020, just as COVID was getting underway there, bridge number 1 suffered a fatigue failure of the stiffening truss. So I mentioned COVID. It's interesting to note that as a result of the border restrictions due to COVID between Chile and Argentina, that additional truck traffic that previously went into Argentina, traveled down past these bridges and then came back in, now suddenly had to go over. So the live load cycling of the bridges increased directly due to COVID. The top chord of bridge number 1 was observed to have suffered a fracture, and the Ministry of Public Works immediately closed the bridge so that emergency repairs could be completed. The ministry reopened the bridge, but placed both load and speed reductions, pending the forensic inspection and analysis of the cause of the fatigue failure, which COWI carried out with our partner RNZ. So here's a photo of the initial fatigue fracture observed in the top chord of the stiffening truss of bridge 1. This fracture was also associated with the complete separation of the field spliced plate welds in the bottom chord of the truss, as well as the cracking observed in this photo of the co-localized vertical truss member. You can see it just at the bottom there by the gusset plate. As both bridges have similar construction and the cause of the fatigue failure was not immediately known, the Ministry of Public Works bundled the 2 bridges together for forensic analysis just out of due diligence, placing the same operational constraints on both in the field, which made a lot of sense. So the ministry requested a full elemental level inspection approach according to the procedures outlined in the AASHTO manual for bridge element inspection. This detailed element level inspection was prepared by COWI from field inspection data, and now will serve the ministry as a new baseline for the bridges. It was used by COWI as a guide for which elements of the bridges needed attention in the near term and which could wait for the future. Having this element level baseline with quantities systematizes future inspections, as you're all aware, and allows the condition states for the bridges to be monitored more effectively. Most elements of both bridges are found currently in condition states corresponding to good or fair condition, with just a few that triggered the need for deeper forensic analysis, and in particular the fatigue fracture site, obviously. So these tables give a sense of the level of effort that was involved in documenting and then characterizing the condition states of all of the elements for these two suspension bridges. It's color coded so you can quickly get a visual of the overall state. They're not in bad shape, except for the fatigue. In order to compare the results of our forensic analysis to actual bridge behavior to make sure that we were representing the structure accurately, COWI developed static and dynamic load testing procedures that were carried out in the field at both of the bridges. So this shows the scales that were brought out to the site to accurately measure the wheel loads of the test truck. This ensured accurate load inputs, as things like fuel weight can obviously vary for a vehicle that has to travel any significant distance in a remote area like this. So we took our measurements right there. Here are some photos of the test vehicle that was used for the static and dynamic load tests. Accelerometers were attached to the bridge that were capable of measuring both vibrations and deflections in the structure, as the load was either placed in a defined location for static load testing or moved along the bridge at defined speeds for dynamic testing. And this is an example of some of the output from the sensors for a static load test on the left and for a dynamic load test on the right. The periods of the various modes of vibration were captured for later post-processing to obtain frequencies for comparison with the theoretical vibration frequency results from COWI's analysis. Following post-processing by one of our sub-consultants, RNZ Engineering, in the field in Chile, who specialized in structural testing, the frequencies were obtained. Here we see the actual field result for the first vertical mode of vibration for bridge number 1 that had the failure, which came in at 0.7 hertz. And here is the actual field result for the first transverse mode of vibration, which also came in at 0.7 hertz for bridge number 1. So we'll compare to these in a moment from our analysis. So next I'll be discussing the finite element model development process we went through, including some discussion on how we tuned the models to more accurately represent field results for the bridges. COWI developed a parametric model for bridge number 1, first using sophisticated structural software, which is very powerful. Due to the similarities in the bridges, we were able to use the parameters we programmed into the code for the first bridge to increase the efficiency of development for the model for bridge number 2. So we leveraged the power of sophistic there. We modeled the cables and introduced stiffness reductions to more accurately represent the behavior of a helically wound wire rope in the field, which is not just the area of the steel. Field survey collected at approximately 6 degrees Celsius, 43 Fahrenheit, was used as the target geometry for the model. A temperature correction was applied using an iterative process with the model and the survey results to bring the model into line with a theoretical original construction temperature of about 59 Fahrenheit. So the modeling was extended to approximate a zero stress truss state that the concrete deck was then loading. This is representative of steel truss segments hung from the main cables and connected together with the field splices during the original construction before the deck was introduced. So I can see some of you wondering what these photos have to do with finite element tuning, which is in fact nothing. These were taken by my colleague who was sent to survey the condition of the bridges, but he came back home with as many pictures of the scenery as he did of the structures. Here you can see the system overview of the model for bridge 1 showing the tower, cables, hangers, truss, deck, and field splices. The deck was modeled as a grillage with transverse stiffness elements introduced but having zero density. The deck in the longitudinal direction was modeled as composite with the stringers. So this is a little schematic of the basic tuning process we developed to match the model geometry to the observed survey. We went through a lot of iterations to get to this. First, the field survey was taken and corrected for that higher initial construction temperature. Next, the truss and cable coordinates were adjusted up to account for future system deflection from the concrete deck after it is added. Then the cables themselves are adjusted in length to create an upward pull on the truss that compensates for the weight of the steel truss to get the system into a zero stress state previously described, as it would have been in initial construction when they first hung the steel segments. So then the system in the model is allowed to fall under the weight of the steel truss and then fall under the weight of the concrete deck to arrive at the finished condition that matches the field survey adjusted to original construction temperature. So as this involves the action of cables, which stiffen with load, the analysis had to be all nonlinear, which added quite a bit of complexity to the project. So we work to approximate the boundary conditions of the actual bridge by empirically tuning springs to represent the friction of the bearings at the end of the truss, so that the model frequency and deflection results would more closely match the load test results. Here you can see the springs represented in green that were modeled at the end of each truss, where it contacts the supports of the towers, and the actual field photo of that is there on the right. We also modeled explicitly the welded field splice plates throughout both bridges in top and bottom chords. You can see here in the middle bay represented on the left, the red circle there. This helped to accurately represent the flow of force through the truss at these locations. Where there were deck joints, we released appropriate degrees of freedom, such as transfer of axial load and moment, to represent the break in the flow of forces at these locations. These releases are shown as orange diamonds in the model capture above for a deck joint in bridge number 1. So how did we do? Here you can see both plots of the matching of the model geometry following all of the tuning procedures I described to the field survey corrected for temperature. On the left is an example of the matching of the floor beam elevations to the survey, and on the right is an example of the matching of the cable elevations at the hangars to the survey of the hanger positions in the field. So very close match in both cases. The model was loaded according to AASHTO procedures with a client-requested HS20 truck, moving live load. So we stepped that along the deck in 3 different positions based on the width of the deck to try to capture the worst case effect. Wind loads were calculated according to AASHTO with actual velocity values obtained from Chilean code NCH432, and they were very high wind loads. A seismic spectral analysis was carried out using a spectrum developed in accordance with the Chilean Highway Manual. So it should be noted that the characteristics of this spectrum are unique to this area of Chile, so it was necessary to use local parameters in the analysis. I think AASHTO would have underestimated. And while this is a load on one of our cables, it is not something we took into account in the analysis. That's just my colleague with his camera. That's how we developed the model and attempted to match its response to the actual field data collected on each bridge. But you might be asking how it turned out. Well, first I'll show you some graphical representations of the various vibration modes in the bridges. Here we have the first 3 vertical modes of vibration from the tune model. And these are exaggerated vertically. This is in galloping Gertie to show more clearly the vibration response. And here on the left is the first transverse vibration mode, and on the right, the first torsional vibration mode. So these are also exaggerated to show the modes very clearly. Here you can see in the middle column the model vibration performance, and the right column shows the post-process frequencies of the same modes of vibration from the field load testing. In all cases, we were able to achieve a very tight match between the field and model results through the nonlinear analysis and tuning, which gave us assurance that the model was representing reality fairly well. And also the corresponding results for the deflection testing we did with that load truck. We placed the test truck at 3 positions: quarter span, mid span, 3/4 span, and then we took the measurement of deflection before and after the bridge reached equilibrium, just to see if there was any hysteresis effects. Measurements were taken before to get the deflection response to the structure. In all cases, our model was able to approximate the deflection results of the actual truck with good accuracy. We were trying to get within 5 to 10%, and we achieved that. This was a major balancing act in the modeling, as it was necessary to tune the stiffness using nonlinear methods to match both the frequency behavior and the deflection behavior of an actual field load test, which was no easy feat. You kind of end up chasing your tail a lot. You get one matched and the other's off, and then you go back and eventually you converge. Now that we had a tuned model that was approximating the actual field behavior of the bridge we felt we could trust, we turned our attention to trying to understand the fatigue fracture that happened, how it happened in the first place and at that specific location, and also to try to understand if there were other vulnerable locations in either of these bridges. The Ministry of Public Works was very interested in that. One thing we took a close look at was the presence of intermediate expansion joints in the concrete decks of both bridges. Bridge number 1 had 5 intermediate deck joints, and all of these were co-localized with welded field splices in the steel trusses, in the same bay as the expansion joint. Bridge number 2 also had 5 intermediate deck joints, and all of these were co-localized with welded field splices. But in the case of bridge number 2, which did not experience any failures to date, the deck joints were 1 bay removed from the field splices. So you can see in the approximate spacing of the first 3 deck joints for scale on a diagram from the model, in the yellow lines there, as well as the appearance of the expansion joint on the deck of the bridge in the photo on the left. And here is shown the specific location that suffered the fatigue fracture, bridge 1. You can see the plates that were added as part of the emergency repair to get the bridge back into service quickly. Tons of plates added on. One thing to note is that the field splice in the bay to the right, the fatigue fracture location, and the concrete bridge deck joint are all co-localized in that same bay. So a lot going on there. When we did our fatigue analysis using the model and the live load demands with the field splices explicitly modeled and the concrete deck joints introduced in the model as releases, it became evident straight away that the tensile stress range in the bottom chord field splice was greatly elevated at locations where concrete deck expansion joints are present. So the top plot is the axial tensile force plot for all bottom chord members, including the splices. And the bottom plot is a subset of that plot showing just the axial tensile force plots for each field splice location, the 9 locations. You can see in the 9 locations with welded field splices that the amount of tension attracted to these splice locations is greatly amplified in the locations where they are co-localized with the 5 concrete deck expansion joint locations, which in the top plot are kind of those dips that you see. Those are the deck joint locations. From our analysis, it is possible to theorize a possible mechanism for what caused the fatigue failure in Bridge 1 in the location shown in this photo. The combined tensile and bending stresses that the deck is trying to carry, they reach that expansion joint, but they cannot cross the other side to continue. They must go into the lower chord and then transfer back into the deck on the other side. So they're resisted by the truss bottom chord, and then they transfer back in. This puts extra stress into the bottom chord, which is what we saw in our detailed modeling analysis. It is possible that the bottom chord field splice separated at its welds first. It was observed to be completely separated when the ministry got there. So once this restraint was lost in the bottom chord, we think that there was a significant global rotation of the truss downward, which then put the top chord into excessive tensile stress, resulting in the fracture that was observed. And that fracture initiated at a weld termination at the top chord gusset plate. But it didn't make sense to us at all at first why we had a fatigue failure in a compression member. So this kind of put all the pieces together. So once we understood more about why the issues occurred, we were able to turn our attention to what we could do about it. As part of the project, we also developed detailed demand envelopes for all members in the bridge using AASHTO at strength, service, and in addition to fatigue. We were able to calculate demand to capacity ratios for every element to determine if other members needed strengthening in addition to the locations prone to fatigue. We also performed an eigenvalue buckling analysis of both bridges and found that the top chords were overstressed for the live load they were required to resist. So the ministry doesn't want to have a load posting on this, as you can understand. So as a result, we developed top chord strengthening measures. Initially, we tried just doubler plates, but we found that it did not provide enough resistance for the elevated out-of-plane bending forces these bridge top chords are subjected to due to their through truss construction with that unbraced top chord. So a subsequent round of design found that adding a channel to the top chord provided the necessary resistance. You can see the parasophistic there with the buckling represented. The bridges were built in segments connected by field splices. The segments are relatively straight, so a stiff channel can be welded to them, no problem. But when you get to a field splice, there is deviation between the sections, so they kind of have a bit of change in slope there. So it's not possible to force a stiff channel to conform to that curvature. So we need to design a way to continue the channel over the splice location. The solution was to bolt a plate with fillers over the field splice, and then bolt 2 vertical plates to the channel either side of the splice, the channel we already welded on. And then whatever geometry results over the splice, the bolted plates and the vertical side plate are then fillet welded together to form an in situ channel to carry the repair over the splice location. But there are some limit states where these chords can see small tensile forces, particularly for wind side loading, and it's a flexible suspension bridge, so there's a lot of unknowns there. And we did not want to introduce a fatigue-prone detail with our top chord strengthening measures. And the way we improved the detail was to weld the majority of the channel length, but bolt the ends to each channel segment. This achieves a category B detail rather than a category E if we were to just weld the channels completely to their ends, which would leave a stress riser with weld terminations. So we avoided that. To address the increase in stress range at the bottom chord field splices, as discussed earlier in the presentation, where we think these fatigue failures are going to initiate first, we designed a bolted splice doubler set of plates that can take the full factored load if the existing welded bottom chord field splices are to fracture from the fatigue effects concentrated there. So this will ensure that the required remaining service life of the bridges can be realized, and it also reduces the likelihood of the fatigue fractures from happening post-repair, as the presence of these additional plates and slip-critical bolted connections serves to lower the stress range acting on the field splices. There's a lot more area at the joint. So these retrofits help all around, both in preventing fracture and also in providing redundancy should that fracture occur. So in conclusion, the Chilean ministry has managed a challenging set of circumstances involving the fatigue failure in Bridge 1 in an unexpected manner. Fortunately, the public has been kept safe throughout the event, and subsequently with the emergency repairs and introduction of service load and speed limits on the bridges, COI carried a detailed inspection per AASHTO bridge element methods and identified the condition states for both bridges. We also performed forensic nonlinear analysis and structural modeling to develop a working theoretical model of both bridges to closely approximate their actual performance in terms of both frequencies and deflection behavior. We uncovered a plausible mechanism for why the fatigue fracture occurred, and then targeted that and developed repairs and retrofits to strengthen the existing members. And in particular, the top chords and the bottom chord field splice locations to restore needed live load capacity and to prevent further fatigue failures from occurring. So thank you for your attention this early in the morning, and I will invite your questions and any discussion. He asked what kind of service life the bridge is expected to achieve after the rehabilitation. We are designing this for 10 years minimum. So I think the ministry recognizes that there could be other issues down the road with such as a flexible structure, so that gives them a nice cushion where they can plan for replacement or whatever they need to do. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.